Hello class, welcome to this lesson 2 on the calculus series, finding limits, graphical and numerical methods. So you can see on the top left, we're looking at a calculus 1 concept since we are in the beginning of the calculus series. Eventually that'll update to calculus 2, calculus 3, and that'll be indicated on the top left, just like it is now when we get later on into the series. So traditionally limits, you might have done limits later on towards the end of pre-calculus. However, technically it's covered in the curriculum in the beginning of calculus 1, and so we're going to go ahead and cover that and introduce ideas of limits. So let's introduce the concept of limits. So let's take this function f of x equals x to the fourth minus 1 over x plus 1. On the top or on the right here, you can see the graph of the function. And you can see that it is undefined. It has a hole at x equals -1. And if you think about it, that makes sense. So if I plugged in, if I were to plug in -1 into the function, then I would get -1 to the fourth minus 1 over 1, or -1 plus 1. And that would give me -1 to the fourth is 1. So you get 1 minus 1 is 0. And you get -1 plus 1 is 0. So that is known as an indeterminate form, but we'll cover that in the future. But for now, you can see that if I plug that point in, it's undefined. It's a hole on the graph, right? So it's actually not defined on the actual graph. So if I graph, for example, the curve, and I choose points -3, -2. And obviously -1 doesn't work, but if I plug in 0 and 1, I just kind of pick points that surround -1. Then I can draw the graph, right? So you can kind of see the points on there. So this is at -1, this is -2. So at -2, we get a value that's all the way down to -15, which is not part of the graph that's shown here because it's all the way down here on this side. But so those are the points. Now the idea is that even though that point does not exist, there is a limit there. There is a value that is present there, and that is sort of like the limits that we are looking at. So what is the limit of the function as it approaches -1? What is the value that it approaches? And that's essentially the idea of the limit. And the notation for the limit is given as follows. So LIM, so the limit as x approaches -1 of the function, and then we need to figure out what that's equal to. Well, you can kind of see from the graph that limit is -4, right? You can see that as x approaches, -1, you're starting to see, well, it's approaching this value here, right? And you can see it visually. But let's take a look at it if I make a table. So if I make a table, and we know that x equals -1 is undefined, and we're going to try to pick some values of x that are very, very close to -1. So we're going to approach -1, but we're going to approach it from the left side first. So if I approach it from the left side, let's pick some values there. So -1.1, -1.01, -1.001. So we want to get as close to -1 as possible approaching from the left, but not actually get there, right? And so if I do that, and then we can also do this from the right side. So let's approach it from the right side, get as close to -1 from the right side of the number line. That's -0.9, -0.99, and so on. -0.999. It's very, very close to -1 without actually being there. And then we're going to plug these points in. If I plug in these x values into the function, so for example, if I plugged in, if I did f of -1.1, and I plugged it in here, then I would get -4.641. And I would continue doing that for all of these. But notice that there's a pattern in the values, right? So as x is getting closer to -1, we're starting to see that this value is approaching a number, -4.6, -4.06, -4.006. And same thing from the right side. If I approach from the right side, it's -3.4, but then it goes up. And we can see that it's approaching that value of -4 that we were talking about earlier. So in that case, what we can say is that the limit is equal to -4. All right, so if I introduce this idea in general, we can say that the limit as x approaches a value c of a function f of x is equal to the limit L. So we can say that the limit is L, some value L, as x approaches some value c. So the limit of f of x as x approaches c, where c is some value on the number line on the x-axis, right, that we're trying to approach. And then that gives us the value L on the y-axis, right, the actual value of the function. But now this is not this value can be non-existent on the actual function, but this is just a limit that it approaches. So as we mentioned earlier in the previous graph, f of -1 was undefined, right? But the limit was defined. Well, the limit had a value. All right, so example 1. So usually in this lesson, we're going to be looking at a graphical or table method, right? So we're going to be using a numerical method using table of values. So let's see what the limit of this function is as x approaches 4. So first off, we're going to make a table and say well, we know at x equals 4, that's the value that we're trying to determine, right? If I plug that value in, notice it's going to be undefined, right? It's not actually going to be a point on the graph, because if I plug it in, if I actually plug in 4, well, I get square root of 4 minus 2 over 4 minus 4. And square root of 4 is 2, so I get 2 minus 2 over 4 minus 4. And so I get the whole 0 over 0 thing, right? And so, that's their question mark there. So if I actually plug it in, it's not going to give me a value. However, I can find the limit, and there's also techniques to do this, which we'll talk about in a future lesson. But if I just plug it in straight in, I'm going to run into issues. So let's approach it from the left and approach it from the right and see what happens. So if I approach it from the left, I get 3.9, 3.99, 3.999, right? Really, really close to 4. If I approach it from the right side, 4.1, 4.01, and 0.001. All right, very close. And then if I plug those values in, so let's say I plugged in 3.9, so I get square root of 3.9 minus 2 over 3.9 minus 4. And I calculate that value. I get 0.2516. And I do that for the rest of them, right? So I can do that on the calculator very easily. I get 0.25 for 3.99. And then let's plug in the numbers on the right side. And notice you're starting to see a pattern here, right? You are starting to see a pattern as we're approaching here, a pattern as we're approaching here. It looks like the pattern is the 0.25 pattern. And so we could say with confidence that the limit as x approaches 4 of the function is 1/4 or 0.25. Remember that if I plug it in, it's undefined. If I actually plug in f at 4, it's going to be undefined. However, the limit exists and it's 1/4. So remember that the existence or lack thereof of the value of a function at x equals a number c has no bearing on the existence of the limit. So the limit can exist. However, the value at that function, right, at x equals c, may not exist, right? Or it may or may not exist. So let's look at an example. This was a piecewise function. So it's saying that it's equal to 2x plus 1 when x is not equal to 3, and it's equal to the value -5 when x equals 3. So if I graph this function, well, you can see this is a line right here, right? So mx plus b, so that's a graph of a line. This is a graph of a constant function. So I know that when I do this graph, when x is not 3, I can graph that, right? So if I were to do a basic graph, we know that the y-intercept of that line is 1, and we know that the slope is 2, so we're going to go up 2 over 1, and we got the graph of our line. But we know that when x is equal to 3, then if I plug that into the line, 2 times 3 plus 1, well, that's going to be 6 plus 1 is 7, but we know it cannot be equal to 7 because x cannot be equal to 3, right? So we're gonna have a hole at 7, essentially. So if so we're gonna have a hole here, and then I can draw the rest of the line. So that's how it's going to look like. And of course it continues down, right? So that's the top part. And then when x is equal to 3, we have a value of -5. So -1, 2, 3, 4, 5. So we're going to have a -5 value somewhere here. okay? And that's essentially the piecewise function if I were to graph it. So we're going to show this here on the slide. In fact, let me erase this here so we can kind of show it on the slide. So there's our piecewise function. And so we know that if at f of 3, well, the value is just going to be -5, right? Because, you know, if f is equal to 3, we know the value has to be -5, right? So that's this value here. And then if I were to find the limit, however, remember the limit indicates, assumes that we're approaching from the left side of 3, right? So we're approaching from the left side, and then we're approaching from the right side. But if we do that, we can only approach that from the graph, right? So we can approach that value. We're approaching that hole. So that's what the limit assumes, is that you're trying to approach from the left, approach from the right, but you're not actually getting to x equals 3, right? And so we're looking at the graphical part, the line part of it. So we know that if I plug in 3 into that portion of the graph, if I plug in 3 into here, then that will give me the value of that limit, right? So we could do that, and we can say, okay, well, it's 2 times 3 plus 1, and that value is just 7, right? So this is 7 right here. So we can plug that in as long as we have a nice idea of what's going on and say that our limit is 7, okay? Of course, we could do a table of values, and if we do a table of values, well, then we're going to get these points on the graph, right? We're going to get points that are on this portion of the graph, points are on this portion of the graph, but then we can see that it's approaching the value of -7. So we might have, for example, 6.5, 7.5, so on, but they're approaching that 7. But this is just a way to kind of look at it in terms of piecewise functions. So some things to keep in mind is that limits do not that there are some limits that don't exist, right? So some limits exist, but some limits fail to exist. And they fail to exist for different reasons, right? So the first reason is that the behavior on the left side does not match the behavior on the right side. So meaning that they don't approach the same value, right? So if I do it from the left side and it approaches a different value than if I approach from the right side, then the limit fails to exist since they don't agree on the behavior. And then the second way that it can exist is if there's no bounds on the limit. So the limit bounds to infinity, or the limit goes to infinity, right? So that's an example of when it fails to exist. And then another reason that they could fail to exist is by oscillations. So if you see oscillating behavior, it's not approaching a specific value, it's oscillating, it's bouncing around to different values, that indicates the limit does not exist. So let's look at an examples of those. So if I look at example 3, I want to find the limit as x approaches -1 of this function here. And it's the absolute value of x plus 1 over x plus 1. So you're going to have to remember the idea of the absolute value. So let's break down the absolute value in terms of its piecewise function. You may recall that the absolute value can be written as a piecewise function, where the value of absolute value of x is equal to -x as long as you have a negative value, and it's x when you have a positive value. So for example, if I had absolute value of -3, well, that's less than 0, right? -3 is less than 0, and so the value of that would be negative x, right? So it'd be -3, which gives me 3. And so that gives me the value of 3 that we want. However, if we had absolute value of 3, well, that's greater than 0, so that's just equal to 3. So this is the -x portion, and then this is the x portion of the piecewise function. All right, so that's how that works. Now, if I generalize that to any piecewise function that looks like this, right, where it's x minus c, well, then it's just the opposite of x minus c, opposite of the quantity x minus c when x is less than c, and it's equal to x minus c when x is greater than or equal to c. All right, so if I do this for x plus 1, right, then it's going to be the opposite of x plus 1. So it's always the opposite of the original function if the function goes negative, right? So the only way that this goes negative is if I say x plus 1 is equal to 0, well then the only way if I solve that for 0, well then x is negative 1. And that's the turning point for the graph, right? So we know that at negative 1, if it's less than that, it's going to go negative. And therefore I include this negative here. And if it's positive after negative 1, then we just leave it as the function, the original function. All right, so that's how that works. So in this case, it's negative 1 for my turning point. So then if I use that piecewise function for the function here, I can plug it into this top part here, right? And in that case, I get this top part, right, divided by x plus 1, and this x plus 1 is from here, right? So we can just take the original function with a negative over x plus 1, the original function just over x plus 1, and then notice that if I do that, I get negative 1 and 1. And so if I were to graph this, well, it's going to look like this, right? So I have the value negative 1 when x is less than negative 1. So when x is to the left of negative 1, the value is just negative 1. But if it's to the right of negative 1, then the value here is just 1. So that's how the function looks like. But notice that the behavior is different on the left side than it is on the right side. If I approach from the left side, I get a value of negative 1. If I approach from the right side, I get a value of 1. And therefore, we can't agree on the behavior of the limit. And therefore, so as we approach from the left side, we get a limit of negative 1. From the right side, we get a limit of 1. So because the values are different, we say that the limit does not exist. And so we usually write this as dne does not exist. All right, so let's look at another example. So we're going to do the limit as x approaches 5 of the function 1 over x minus 5. So let's do this with, so the piecewise function, we can kind of graph it because it's very simple with the absolute value by using the definition of absolute value. With this one, we probably want to plug in values to see how it looks like. It's not a difficult graph to graph, so we'll actually show you the graph of this as well. But first, let's just do a table. We know that if I plug in x equals 5, if I start doing that, well, 1 over 5 minus 5, that's 1 over 0. And we know that 1 over 0 is undefined. So division by 0, right? So we have undefined here. So then let's see what the behavior looks like if I approach from the left side. So 4, 4.5, 4.9. And then let's do it from the right side. If I plug in, for example, 4, well, it's going to be 1 over 4 minus 5, which is 1 over negative 1, which is negative 1. So I can plug that in, negative 1. If I plug in the other values, I get negative 2, negative 10. And then if I plug in the other values from the right side, I get the same because it's a symmetric graph. All right, so in this case, if I plug in x equals let's go ahead and actually see what happens, because if I look at the behavior on the left side, it doesn't look like it. If I look at this behavior, it looks like it's getting more in the negative. If I look at the behavior here, it looks like it's getting more in the positive. So it looks like it's growing, right? For 1, 2, 10, negative 1, negative 2, negative 10 is going down there. So we need to see if there's more, if there's a pattern or if it's continuously growing. So let's go to 4.9, 4.99, and then 999. And then we're going to get even closer on the right side as well. If I plug in 4.9, well, we already know that that's negative 10. But if I plug in the other ones, look, the values are growing. They're actually getting bigger and bigger. If I do this on the right side, they're getting bigger and bigger as well. And we can see that the values are unbounded. They're getting larger in the positive or in the negative side as we approach 5 from either end, and therefore the limit does not exist, right? So we're going to say the limit does not exist here. So there's two reasons. It's unbounded. In addition, it's going in opposite directions. One is going to negative infinity, the other is going to positive infinity. If you think about it, that makes sense. If I were to graph this function, right, then the graph of that function it's a hyperbola, right? So if I were to graph that 1, 2, 3, 4, 5, it's a hyperbola that's been translated 5 units to the right. And so if I were to graph this, in this case, normally if I were to graph the hyperbola, it would look like this, right? But it's translated to the right. So we have a vertical asymptote at 5, and so we have something that looks like that, right? So this is 1 over x, and then this is 1 over x minus 5. So we can see that as we approach from the right side, it's going to positive infinity. As we approach from the left side, it's going down to negative infinity. It's getting big. It's getting, more negative from the left side, more positive from the right side. All right. So let's look at an example with a different kind of behavior. So let's approach this from the left side, and let's just do a table that approaches it from the left side. So if I look at x equals 0 on the right side of the table, because we're approaching it from the left here, right? So we're approaching 0 from the left. Well then, and we know if I plug in 0 here, if I do cosine of 1 over 0, well, we can't divide by 0. So 1 divided by 0, that's going to be undefined. All right, so in that case, we got undefined for that. So let's plug in a lot of numbers and get as close to 0 as possible. So starting with -1/2, -1/4, -1/10, right, and so on and so forth until we get really close to 0. But let's take a look at these values. So if I plug in x equals -0.5, cosine of 1 over -0.5, well, -0.5 is -1/2. So this is going to be cosine of -2, right? And I plug that into the calculator. Okay, you're assuming that these values are in radians, right? So cosine of -2, where -2 is in radians. So if I plug that into the calculator, I get -0.994 for that. But if I keep going, notice the values, right? So it looks like it's approaching something here, but then it goes from negative to positive. So it's oscillating. It's staying positive here, but it's changing to a different value. But then it goes to negative here, right? And then it goes back to positive. So you can see there's oscillating behavior here. So this indicates oscillation. All right, if I approach from the right, and so x equals 0 is going to be on the left side because we're approaching things from the right. So we're going here and we're getting as close to that as possible. So if I do that, well, then look at the values here. It's going to be the same as the values from the left because cosine is a symmetric curve, right? So it's going to be the same values. It's going to have the same, values that you see. So there's that oscillation going on, positive, negative, positive, so on and so forth. So because the values seem to oscillate on the left and the right side, they don't approach any single value. So we indicate that the limit does not exist as well. All right, and here's how the graph looks like for cosine of 1 over x. So you can see as we start approaching x equals 0, things start happening to the graph, right? So it starts having that wild oscillating behavior, right? That you can see in there, and that's because the limit does not exist. All right, so that is it for the lesson. So now we're going to do some review questions. So I highly suggest for this portion of the video that you write down the questions and attempt to solve them. You're going to need a calculator for this to plug in these values. So you can pause the video and then we'll go over it. All right, so assuming that you kind of looked at the questions, let's take a look at them together here. So actually, let's take a look. Let's go to the review parts 2. Let's look at the other questions here. So go ahead, like before, go ahead and pause the video, write these questions down, and see if you can solve them before we go over them. All right, so assuming that you pause the video, let's take a look at the first question. So if I do the very first question in the first slide of the review, if I plug in those values, we know that we can't plug anything at 3 because it's going to be, undefined. But if I plug in the values from the left side, I get those decimals. If I plug into the right side, I get those decimals. So we can kind of see that the limit as x approaches 3 of that function is, if you look at the values on the left side here, on the right side, it looks like it's approaching 0.0625, right? But negative. negative 0.06250. And so that's what we get here. And then that actually turns out to be 1 over 16. If I look at the second problem on the first slide, sine x over x, so as x approaches 0, this value, you actually have a limit for this, surprisingly enough. But if you plug it in from the left and from the right side, you plug in those values, you can see that, yeah, this is approaching 0.99999, so that's basically 1, right? So it's approaching 1. And we can see that this is actually really, really close to 1, that we ended up rounding it to 1. So that's 0.9999 as well. So the limit has to be 1. All right, even though that value does not exist, right? There's a hole in that graph. We know that the limit exists, right? So there's a difference there. All right, so let's look at the second slide, those questions there. So for this, it helps to either do the graph or do the table of values. So I'm going to show you this with the graph. So let's graph the first part. So if I graph f of x equals x squared plus 3 when x is not equal to 1, and it's 2 when x equals 1. So if I were to graph this, well, x squared is a parabola, so we know that it looks like this, right? But it's shifted up 3. So it's a parabola shifted up 3. So we know it's the y-intercept is 3, and then it's growing, right? So when x is equal to 1, if I plug in 1 into here, right, then I get 1 squared plus 3, which is 4, but this cannot equal to 4, right? So here we got 4, but it cannot equal to 4, so it's a hole. But when x equals 1, you get the value 2. So that's how the graph looks like. It's good to practice graphing it and visualizing it. However, you don't need the graph to be able to do this. We know that f of 1 is 2, right? So f of 1 is 2. However, the limit as x approaches 1 is 4, because you can see from the graph, the behavior as you approach from the left and from the right side, it's approaching that limit value of 4. And you can get that simply by plugging in 1 into this part of the function. All right, so when it comes to the piecewise functions, where you see it's not equal to 1, and you see a graph or a function rather than just a constant value, right? A variable, rather than just seeing that constant value, then that indicates you can, most of the time you can, if you have the visual of it, you can kind of see that, oh, I just need to plug in the value into that portion of the function. Now for the second part of the second limit here, if I notice that if I were to graph 2 over x minus 5, that's like the hyperbola that we had before, right? So if I were to graph 2, so it has a vertical asymptote x equals 5, and it looks kind of like this, right? It's similar to the one that we had in the other question, but this time you had that 2 there, but it doesn't matter, that 2 doesn't change anything. So if I do a table of values there, you're going to see that it's going to be growing from the right side, and it's going to be going down from the left side, and so the limit does not exist here. Okay, so this one, the limit does not exist. So if I look at the next one, so again, I can plug in values for here to get that it does not exist, but I just wanted to show the function. All right, so for this one, we can also plug in values to show that it does not exist, or we can look at the graph. So if you know how the graph of tangent looks like, well, let's graph it. We know that tangent, remember that tangent is sine over cosine, right? So tangent is sine x over cosine x. So if I were to graph, well, we know cosine x is 0 when x is pi over 2. So every time we have pi over 2, we have a vertical asymptote, right? Every pi over 2, there's going to be a vertical asymptote. And so at negative pi over 2, there's going to also be a vertical asymptote. And so we know the graph of tangent kind of looks like this, right? And it repeats. So there's another tangent on this side, and so on and so forth. So that's the graph of tangent x. Well, then as x approaches pi over 2, well, we know that if we approach pi over 2 from the left side, the graph is going up to infinity. as we approach pi over 2 from the right side, the graph goes down to negative infinity, right? It's going down, down, down. It's not approaching any particular value. It's just getting more and more negative from the right side and more positive from the left side. So we can clearly see that this graph does not exist, or the limit does not exist. We're going to say that does not exist. And again, you can do this by plugging in values. So, you know, plug in a bunch of values to the left of pi over 2, plug in a bunch of values to the right of pi over 2, and then you start seeing that the values are blowing up. All right. But this is just a quick way of doing it, just looking at it graphically. All right, so that's the end of lesson 2. I hope you found this video informative, and as usual, I'll see you in the next one.